This is Joel, and in this video we'll be talking about asymmetric routing and unknown unicast flooding. A bit of context here. I was recently asked about this scenario, and to be honest, it's been a while since I came across such a problem, so I kind of completely froze for a few minutes. And I'll tell you the reason as well, maybe at the end of the video, on why you don't see this scenario in nowadays, in the current networks. Nevertheless, it's a very interesting scenario, and I think if you're still managing some of the legacy switches, right, like 3750s and so on, then you might still encounter this scenario, right? So let's quickly recreate it, right, in this simple topology, and then finally let's also put a fix in place to kind of prevent this scenario from happening in a actual network. Okay. So let me talk about the topology which I've already set up here, right? I'll not configure the topology end to end, right? It's already been set up. So what do we have, right? So we have a VLAN, right? So think of this as a typical campus network, right? So you've got your access layer switches here, you've got your distribution, and then it connects to probably a core of the network, and connects to then maybe you have internet host or whatever, right? Connects to your data center or maybe to the internet, right? But the whole idea here is you've got a particular host, right? 10.1.1.10 in VLAN 10, right? This particular port is in VLAN 10. These are trunk ports, right? This one is also a trunk port. These are routed ports, right? So we have point-to-point /30 IP addresses here, right? So these are all routed ports, and we have we have EIGRP, right? The routing which is already set up. Okay. The only thing which you really need to know is the other important thing is the HSRP part. So I've also set up HSRP because if you look at it from this switch, right, for this particular host, we want to give redundancy when it comes to the default gateway, right? That's the whole purpose of HSRP, right? So here in this case, I have made R1 as my primary primary HSRP router, and the R2 is going to be the standby. Okay, and in HSRP you normally have a virtual IP that is the 10.1.1.1, right? So that's configured as the gateway on the H1. Okay, the only other thing which you need to know is what I've also done here is because I want to create this asymmetric scenario, what I've done is I've increased the bandwidth on this particular link, right? Why? Because I want R3 to pick this particular link, right, for the return traffic. And let me explain. So when H1, right, wants to when this 10.1.1.10 wants to talk to 10.2.2.10, what really happens, right? So you have, because these two are in two different subnets, there is going to be a ARP request which is sent by H1, right? It is going to send a ARP request to what? The default gateway, which is 10.1.1. It will get the ARP reply, and from there it is going to forward the traffic to to R1, right? And R1 is obviously going to route this traffic to R3, right? And then ultimately it goes to your H3. Reverse traffic comes here. Now on R3, it can either go like this or it can go like this, right? If it is going in this direction, then it is no longer asymmetric routing, right? When you have asymmetric routing is going to be present if it takes this path, the second path, right? Which is this one, right? So that's why what I've done is I've deliberately increase the bandwidth on this link so that EIGRP now will pick this link, right, for the return traffic. Okay, so once the traffic comes on to R2, it should ideally forward it on this link and come down to my H1. That is how it is supposed to behave, right? At least this topology. I have deliberately set it up like this because I want to recreate the whole asymmetric routing scenario. Okay. So what we'll do now is I'm going to have a couple of packet captures, right? Still, actually, I mean, we just talked about asymmetric routing here. We still haven't gotten to the actual problem, right? Asymmetric routing, I mean, it's the problem, but we haven't gotten to the actual, what is this outcome of this problem, which is the unknown unicast, right? We'll get to that in a minute. But before that, what I want to do is let's probably send some packets from H1 to H3, and let's do some packet capture. So we'll do a packet capture here on this link. We'll do it on this one, and we'll do it on this one, right? and we'll look at the packet captures to get a much more understanding of this particular topology. Okay, so hold on tight, whereas let me grab my packet captures, one sec. All right, so I've started my packet captures here. So just to give you an idea here, so I have 3 packet captures, 1, 2 and 3, right? So there are 2 here, stacked windows. So the one on the left hand side is the packet capture here on the host interface, and then like I spoke, right, we have 2 more packet captures. This one, the cross link, is the one on the top, and the straight link below is the one on the bottom, right? So that's the packet captures. So we have them running in the background. What we'll do now is we'll start some pings from H1 and we'll send them towards H3. Let's send those pings. Let me go on to my terminal here. Yeah. So before we send the pings, let's just make sure, let's observe, because what is important for us here is the ARP table and the MAC address table of what? This R2. Okay. So let's just observe, let's go into R2 and let's observe what is the show IP ARP, right? This is the ARP table as of now. Show MAC address table, right? There you go, right? And just observe that this particular IP, which is 10.1.1.10, and this particular MAC address, which is ending with 6000, you don't find it here. You don't find it in the ARP table, you don't find it in the MAC address table. Great. So what I'll do now is I'll just go, and there is a VLAN which I had shut, right? Now I'll unshut the VLAN and let's get to the testing, right? So I'm going to do a no shut on it. You might see some gratuitous ARP here on the top, which is fine, right? Over here, that's basically 10.1.1.3, which is basically the VLAN 10, sending a gratuitous ARP, right? It's basically announcing to the world that, hey, look, I'm back online, right? Don't worry about it, not very relevant to us. But apart from that, you don't see any other activity throughout the packet captures, right? On all the 3. Great. So let's now do that ping, right? So let's do a ping 10.2.2.10, right? We are pinging from H1 to the host on the outside. So there you go. The ping is done, successful, awesome. Now let's try to analyze here. See what happened on, and now let's also look at R2 as well here on the left hand side. First, let's look at R2. Show IP ARP, right? You can see there is a ARP entry for 10.1.1.10, right? And its associated MAC address. Let's look at show MAC address table. And there you go. We have the entry in the MAC address table as well. Great, right? And how did this really happen? You can see in the packet capture, there is a ARP request here, which came in, right? So you can see clearly, it says it's a request, ARP request. Who sent the ARP request? It was sent by, if you see this MAC address ending with 84000, that is nothing but the MAC address of my R2's VLAN, right? So maybe we can have a look at that. It is basically show interface VLAN 10, right? You see here, this is the MAC address, right? So this is clearly ARP request which came from R2, right? And the host promptly replied with the response as well, right? Now because this ARP reply was sent by the host to R2, as a result of that, what happened? R2's ARP table was updated with this particular entry, and you also know that how does switch operate, right? Switch always operates using source learning. So because of that, there was source learning as well, right? Because R2 saw the ARP reply come back, right? It was able to understand, it was able to update its MAC address table that, look, H1 is reachable through port Ethernet 0/1, right? So that's how everything worked, which is great. Till now, there is no problem. This is all working fine. There is no flood, right? You don't see any flood. So this is good, right, as of now. Now what we'll do is, I'll pause the video now for about 5 minutes, right? And I'll not tell you why we are doing this, right? I'll pause it. And the very next, when we come back after that 5 minutes, what we'll do is we'll do the ping again and we'll see the difference, right? We'll do the same ping again and we'll see the difference. Right now, you see, observe this. What has happened is when we did the ping, the ICMP, reply, as you see here, the return packet, right here, was seen only in this particular packet capture, right? You can see the below packet capture is empty, right? If I have to explain that using this diagram here, what really happened? Let's just grab this pen. So packet went in this direction, it went all the way like this, it went to R2, and when packet came to R2 did a, because when the packet came to R2, the source address was this, the destination address was this, right? And R2 also knows the source MAC address, but it did not know the destination MAC address, right? Because its CAM table or MAC address table was empty. So it did a ARP request, it got ARP reply, right? And as a result, it was able to then forward the packet properly in this direction to this guy, right? And that all worked fine, right? This is how it worked. But let's see what is going to happen when we come back in exactly 5 minutes, right? We'll come back in 5 minutes and let's see what is going to happen. How is this going to change, right? Yeah, so let's come back. I'm going to pause the video now. All right. So 5 minutes has passed and we are back. And what I want to show you quickly here is, so this is the output of the show MAC address table, right? Before we went, for that break. And now I just ran the show MAC address table. I can run it once again, right? You can see what has happened. Our entry has disappeared, right? The entry for H1 has disappeared. Okay, but let's also observe what's happening with ARP table. There you go. The ARP table still has the entry, right, for 10.1.1.10. But you see this particular MAC address is no longer present here in the MAC address table. Now let's see what is going to happen because of this, right? Let's go back to our ping. Let's go back to our ping. And just to recap again, when we did the ping last time, you see what has happened. There was no activity on this particular interface, right? There was no there was no activity on which interface? On this interface, the interface facing down, right, from switch 2, or basically this interface as well, sorry, the interface facing down from R2, that is Ethernet 0/0, there was no activity. But now let's observe. So let's get into the terminal. It's my terminal, right? And let's do that ping, right? Let's do the same 5 packets again. And voila. Can you see what's happened? This time when we did the ping, what happened? You see those the 5 packets have come here on this interface. They also have come on this interface, right? So that's interesting, isn't it? And why it's a problem? I'll tell you why it's a problem. Now let's, instead of sending 5 packets, let's repeat this for, I don't know, maybe 100 packets, right? And then let me try to keep this side a little bit on the side, right? So keep observing these 2 packet captures, because that's where all the fun is, right? Keep observing this packet captures. What you see the numbers here on the top, it is 1648, and here the number is 1605. I'm going to send 100 packets and see. Can you see the packets are increasing, right, on both the interfaces? Let's send 100 more, and there you go. Right, you can observe the numbers, right? The number is now 2019 and 1976. Let's send 100 more, and you can see again the packets are increasing. So you get the gist, right? What's happening is now, right, after 5 minutes, our router R2 is actually flooding. It is not sending the packet only on this link, but it is also sending on this link. If it had more links, it would basically flood on those links as well. So now we have reached the problem associated with this scenario, which is the unknown unicast, right? And why is this happening is because, I think you might have already guessed it, and the reason is because of the discrepancy of the ARP table and the MAC address table, right? So what is happening is, since, right, let me grab my pen, since now, right, if you look on R2, we saw that the ARP table is still there, right? The ARP table has the entry, right? And the reason is because in Cisco devices, right, the ARP table is kept for 4 hours by default, right? It is maintained, the ARP table is maintained for 4 hours, whereas the CAM table, right, is maintained only for 5 minutes, right? After 5 minutes, right, the CAM table is flushed out, and as a result, what really happens, but the ARP table is retained for 4 hours, right? So what is happening here is when the packet is coming now on R2 is not initiating the ARP request which it did earlier. Which is the ARP request? Remember here in the packet capture we saw the ARP request, right? This ARP request, right? And the ARP reply, that is not happening, right? Why it is not happening? Because it already has the ARP entry from the 4 hours because it is going to be there for 4 hours, which it did a few minutes back, right? So it is not doing this ARP request, right? Because it is not doing the ARP request, it's my pen, yeah. Because it is not doing the ARP request, right? The R2 is not able to get the ARP reply, and ultimately R2 is not able to update its cam table, right? Because of this, now R2 has no way of understanding that H1 is reachable through this link, right? R2 has no way, because for the next 4 hours it will not be able to learn about this particular host, right? So for the next 4 hours until that ARP entry is flushed out, right, what R2 will do is every time you send any packet to R2 towards this H1, it will flood it. It will flood it on all the interfaces except the interface on which it came, right? This is not a good scenario, right? Because this can really clog your whole network. Imagine someone is trying to, I don't know, maybe from this server H1, let's say they are trying to, download a very big file, right? Or say if they are trying to download a big file from H3, my bad, right? So there's going to be a lot of traffic on this particular interface, and not just this interface. You might have many other interfaces like this, right? So on all these interfaces, you will end up getting traffic, right? Which you shouldn't be getting, right? And you might end up clogging the whole links, because of this scenario, right? So that's the problem, and we understood the situation why it is caused as well. Okay, now how do we solve this, right? If you want, take a pause the video and think for a solution, right? But yeah, how do you solve this? The problem, the solution is actually pretty simple. All you have to do is make sure that the ARP entry is also flushed every 4 minutes, or you can do the other way around as well. You can make sure that the cam entry, which was getting flushed in every 5 seconds, you can make sure that the cam entry or the MAC address table is maintained for 4 hours. You can do either of them, right? All you have to do is you need to make sure that I don't know what's happening with my pen, but you need to make sure that the 2 tables which we just now saw, let's go back to my CLI, right? These 2 tables, right? The MAC address table and the ARP table, right? They need to flush, they need to flush at the same time, right? The timer should be similar, right? That way what will happen is that the ARP entry will not exist. If the ARP entry is not existing, then it will force R2 to do an ARP request, and that will enable the MAC address table to be populated, right, with the correct value. So let's add this, right? Let's add this solution. So how do we do this? Very simple. So we will get into the interface, which is interface VLAN 10, right? And in this case, like I said, I'm going to change the ARP timer, and I will make it equal to, in fact, before I change it, let me show you where you can find it. Let me show you where you can find these details, right? So if I do show interface VLAN 10, right, you can see there is a value here. ARP timeout is 4 hours, right? Similarly, if you want to see the MAC address table, so MAC address table, I think there is a aging time, right? And you can see the time is 300 seconds here. All we are doing right now is we are going to map them, or we are going to make sure both of them are equal, right? So let's get into configure interface VLAN 10. Okay, so we are inside VLAN 10. Let's go to ARP timeout, and I'm going to change this to 300, right? So I've gone and changed that to 300, and as soon as I do that, technically you should, I think there is a request which went in directly as soon as I changed that, right? And now let's go back and see what has happened with the show IP ARP, right? So ARP table is still there, but you see it got populated just now. You can see that age is 0 minutes. Let's look at the MAC address table, right? So in the MAC address table as well, you should see the entry populated now, right? So now we will never hit this issue, right? because what is happening is our ARP table and the MAC address table are getting flushed, right, in 300 seconds, right? So every 300 seconds there is a new ARP request like this, and there will be ARP reply as well, and using this ARP reply our R2 is able to learn the MAC address, right? Now let's try the same thing. Let's try the same ping. Let's see what's going to happen. Let me minimize this, right? Let's just look at the packet capture on the right hand side, and let me try to do a ping here, right? So let's do the ping this time, right? Just observe both these packet captures. You should see that the above packet capture should increase, because above packet capture resembles this link, the link Ethernet 0/1, whereas the below link should not get any packets this time, right? So observe the number as 2095, that will not increase, whereas 2137 will increase, right? There you go. The number here increased to 3445, whereas this has not increased. Let's send 100 more packets, right? There you go. The packet numbers increase here but did not increase here. So you get the point. The solution was very simple. What was really happening was, on R2 the ARP table was not timing out, whereas the CAM table was timing out, and because the CAM table was timing out, the switch, or in this case R2, did not really know where to send this frame, right? It already has the MAC address, because it has already done the ARP before, so it is not going to do an ARP again. It already has it, but it did not learn about the MAC address, so as a result it was not able to update its CAM table, right? So that was the trick here, right? Just matching the ARP timer with the MAC address aging time, we were able to fix this scenario. So hope that was useful. This is, like I said, it's a very very simple scenario as such, but again, coming to why I had forgotten this scenario is because in the current networks you don't really come across this a lot, because generally you don't, at least the networks which I manage, I haven't seen HSRP being used in a while, right? We use what we call as we use virtualization technologies like VSS, right, or SVL, right, and virtual switch system. I think that's, you can look it up, but basically it's a way of logically putting together both the boxes, right? As a result, what really happens is you will not have R1 and R2 active at the same time. So there'll be only one single router which is active at the same time. So as a result, you will not have the scenario of asymmetric routing at all when you're using VSS and SVL, right? So as a result, you will not see this scenario a lot if you're running some of those technologies. But yeah, I mean, I'm pretty sure there are a lot of people out there who run 3750s and so on, right? So, and you'll be doing HSRP and so on. So this is a scenario you need to watch out for. But then, yeah, the fix is very simple, right? So hope you guys like that, and have a good one. Bye.